So let's just pick up where we left off. Okay, so what I've shown you up to this point is two stylized facts. There is exceptionally low mobility in India, and there is this exceptionally large rural-urban wage gap, right? And our explanation for this is, as I said, based on this combination of well-functioning rural caste-based networks and the absence of formal insurance, okay? And the basic idea here is that if a household sends one or more of its adult males permanently to the city, then, and it's treated as a unit by the network, then it's going to have a harder problem maintaining the same levels of commitment. You're going to have information problems. And for all of these reasons, it's going to lose access to this insurance arrangement. And if this effect is sufficiently large, then you might actually end up leaving money on the table in some sense. You might just choose to forego the extra income that you get by moving to the city. Okay? Now, this is a story that we tell, and I've given you some descriptive evidence suggesting that these networks actually work quite well. Okay? Now, how do you actually test this hypothesis? There may be other explanations for why you see these particular patterns in India. And I'm going to talk about alternative explanations as we move along, right? So what we're going to do, this is the strategy. What we're going to do is to try to derive additional tests. And this is what you would want to do as well, right? I mean, if you write a paper, you want to derive some tests from the theory that allows you to actually distinguish your story from alternative stories, right? So what would be the simplest test of our hypothesis? Well, if our story is really a story about these well-functioning caste networks, in some sense, not restricting, but reducing the incentive of people to leave and go to the city, then what you'd use is variation in the strength or the performance of these networks, right? Now, if, for example, there were some populations that had access to these networks and other populations did not, then you could just see whether, in fact, those populations which did not have access to these networks had higher rates of migration. Now, what's one obvious problem with this kind of strategy? Can you tell me? So those of you who, just... Exactly. So one issue here is that it's clearly not random. You would think that a place which did not have access, a population which did not have access to these networks is different on other dimensions as well, right? And that's going to always be a problem with observational data, and we'll talk about how you actually test as we move along. But that's something to think about, is that you might have the test, but you must always be thinking in terms of some kind of exogenous variation. Otherwise, obviously, it's not going to work very well, right? But in our case, there's an additional problem apart from the issue of identification, which is that in fact these caste networks are pervasive. And it's not just in Hindu society. So if you look in India, even non-Hindu populations will have social structures which are sort of equivalent to a caste. So I am not Hindu, I'm not Muslim, I'm not Christian, I'm something completely different, but then my community still marries amongst themselves, or at least not anymore, but historically. So we look very much like a caste. We're not technically a caste because we're not Hindu, but we would still behave in the same way that this model would predict. And it's the same story, for example, for Christians who are converted from other castes. They will still know what caste they were actually originally from, and they will still marry within those same original castes. So in that sense, nothing is, there's no sort of, we could not use, for example, religion as a way of actually testing this either. Okay? So what we do in the paper is an alternative. Instead of looking across groups to test our hypothesis, we look within the caste itself. And what we do is to theoretically derive which households within the caste would benefit, for example, more from this caste network. And then we test whether it's precisely those households who are less likely to have migrant members. And we have an alternative test where we identify in another dimension which castes benefit less from this network. And we see whether, in fact, those households are more likely to have migrant members. Now, you still have the same problem that you brought up. I mean, you might say, well, okay, these castes might benefit more or less from, the network, and therefore we can test whether, in fact, those households have more or less migrants. But those households could be different other dimensions as well, and which is why they have more or less migration. So when you do the empirical analysis, we've got to keep track of all of these things, okay? And you will see as we do it, the advantage of having a theoretical foundation is that it becomes really clear what your identifying assumptions are, what is going on, what you need to worry about, etc. And you'll see that as we go forward, okay? So for those of you who want to do empirical work, I mean, the one word of advice I would have for you is always think about, don't just write down a theoretical model and hope that you will get the data one day to test it. But keep the two things in your mind as you go forward. Think about the theory and think about the empirical work in tandem, okay? Because that's the only way to actually make, I think, substantial progress, okay? So as I said, the strategy here is to try to identify which households within this community are going to benefit more or less from the network. And the only way to do that, of course, is to write down a model of mutual insurance, right? And as I told you earlier, there is a sort of huge literature on mutual insurance, right? And I sort of set up the foundation for you with this sort of, the test of full risk sharing. From there, that literature has gone in different directions, mostly thinking about partial risk sharing. But the whole literature basically assumes that there's a fixed set of people in the arrangement, and it will typically assume that lambda, that sharing rule, is exogenously determined. It's just predetermined. Now, when you have partial risk sharing, of course, in certain states of nature, when the participation constraint is binding, then, of course, lambda is going to be determined endogenously, right, based on the participation constraint itself. But where the participation constraint is not binding, in all of these models, the lambda just comes from heaven, right? You have no idea where that thing came from. Now, in our case, of course, it's a different story because we're looking at this decision of a household about whether it wants to participate in the network or whether it wants to take advantage of these urban opportunities and send one or more of its adult members to the city. So what we have to do is to endogenize, we have to take a step back and actually model the ex ante participation decision. So we're going to endogenize the number of people who will participate in this arrangement. We will also endogenize the risk sharing, the income sharing rule, the lambdas. And in fact, that's what's going to tell us which households will benefit more or less from this network in equilibrium, and therefore which households are more or less likely to have migrant members. Is that clear to all of you, the strategy here? We're going to be actually using the theory to actually identify which household would be at the most, in some sense, the greatest risk of sending someone to the city, based on how much they benefit from the network, okay? All right, so now let's just go through the setup. Okay, so let's start off with the income generating process. We're going to make it very simple. I remember the simple example that I had earlier with two individuals and two income realizations. We're just going to generalize that, and we're going to allow for many states of many individuals and many states of nature. But we're going to still assume that in fact income realizations are independent across individuals as well as over time. And you'll see that this is going to help us in terms of solving the model. Okay. Now, if you look at the sort of the insurance literature, they will often be more general than that. We're going to just go with this simple setup. Okay. Now, each household is going to be the decision-making unit. So when we think about this person leaving to go to the city, when we think about remittances, all that is within the context of this household, which we're going to basically ignore intra-household bargaining, intra-household commitment problems. I mean, there's a whole literature on that too, about how migrants will go to the city and then basically lie to their families about how much they earn, for example. We're going to sweep that away because we're interested more in the inter-household, the interaction between households in the community. So within each household, we're going to assume that there's no issues at all. There are no commitment problems, there are no information problems. It's literally one unit. Okay? Now, each household derives income from its local activities. So if it's a land-owning household, for example, it's going to get profit from its land. If it has a bunch of adult workers, it's going to get the agricultural wage. Again, we're not going to get into the details of what the household composition is like. There's just basically a household, that's the unit, and it gets a certain income from its local activities. Okay, and as I said, the income varies independently across households in this community, which in the Indian context would be the caste, we're going to assume. As well as over time. Okay? And in addition, one or more members of this household will receive a job opportunity in the city. And just to be clear, this is not about shocks. Okay? So that whole literature on insurance is about these income shocks and how much you can smooth your consumption, right? Here we're thinking about someone in period 0, the beginning of time, deciding whether or not they want to be part of this thing. Once they've decided to be part of it, of course, all their subsequent shocks will be smoothed out, etc., etc. Okay? For our purpose, the idea is that at that initial point in time, this household, one or more of its adult members, will receive some opportunity in the city. And that's private information to that household. They know what they could earn by moving to the city. Okay? And the decision for the household is whether to send these people to the city or not. Okay, that's the key decision. Okay. So again, here's an assumption that's going to simplify life for you. We're going to assume that the household has logarithmic preferences. Okay. So this allows us to express the expected utility from consumption C as an additively separable function of mean consumption M. So you guys should keep track of the notation a little bit because this will come up again. Okay. So M is your mean consumption. Okay. And V is the variance of your consumption. If you just take a Taylor expansion, you stop after the first two terms, you're going to end up with this. Okay, so the second term here, we're going to call that the normalized risk. This is just the coefficient of variation squared. Okay, that's all it is. The variance of consumption divided by the mean consumption squared. But you can see that you have this very nice structure, this separable structure, which is going to help us a lot in solving out the model. Okay, so the first term is your mean consumption. Of course, the more you have, the better off you are. The second term is your risk term. The more risk you're facing, the worse off you are. So if you were in autarky, for example, you had no access to anything else, then your consumption and your income would be exactly the same, right? Because remember, we have this assumption here that you have no saving and no storage. So then this would reflect not the risk, your consumption risk, but this would be literally your income risk. Okay, and you'll see that as we go forward. The two will be interchangeable when you're in autarky. Okay. Okay. So now let's talk about the risk sharing. So we've talked about this earlier. Given that these households are risk averse, they have these log preferences. Given that your income is changing over time, you would like to smooth out your consumption. Okay, and what this household is going to do, of course, if it joins this insurance network, is to smooth out its consumption. It's going to be better off. Okay, now the one assumption that we're going to make, which is going to make our life much simpler, is that we're going to assume that there is full risk sharing ex post. And I talked about this earlier as well, about how there is this whole literature which talks about partial risk sharing, right? But at the same time, we know, I showed you some results from Townsend's paper earlier, but there have been many other studies that have followed, and all of them basically find extremely high levels of ex post risk sharing. And so what I'm going to assume is that you in fact have full risk sharing ex post. Okay? This is a simplifying assumption, but that's going to make things much easier for us analytically. And again, these are choices that you have to make. And my view is always that you go with the simplest assumption, so you actually end up with something which is tractable, analytical, and which you can then actually say something about, where you have some intuition. Okay, so this is going to be an important assumption for us, as you will see. Okay. Okay, so we talked a bit about this idea that when a household has migrant members, it won't be able to commit at the same level as it used to earlier. And the basic idea that we have here is that, look, the way that you support commitment is through these punishments. So why is this caste network so effective? Why is it that typically you organize insurance networks around social groups? The reason is because when these people deviate, when they don't give in the money when they're supposed to, it's not just that they lose the service of the network in the future, they also get sanctioned, they also get punished. And what's nice about the caste network is that this thing has been in place for so long that you're connected to so many different people. Within the village, you have this sort of spatial segregation on caste lines. So you're always interacting with people from your own caste. So now the loss to you, if you get sanctioned, for example, can be enormous. If people stop interacting with you, there's no one else for you to interact with. You're really screwed, right? So you can imagine that these networks can really punish people very effectively. Now they can only punish them effectively when they're there, when they're interacting with them. If I'm sitting in England or in America, my network can't punish me, right? It's in India. I'm not even interacting with them. They can't really hurt me anyway. And that is the idea over here, is that when this person has moved to the city, that particular individual for sure you cannot punish. Now you can still punish his family, right? In some sense they're like social collateral. You can really hurt them, and if he cares about his family, then there is that ability to punish these people. But the point is, it can never be at the same level as another household where everybody is in the village and available for punishment. The other issue which is related to this is that if you kick these people out, the people in the rural area are still going to have now this urban connection. So their outside options have gone up. So when they go into autarky, in fact, they're not as badly off as a household which is completely based in the village. They have other opportunities. They can smooth out their income through sending this person to the city and so forth. So that household in general is going to be better off in autarky too, if it's kicked out. So for all of these reasons, the household's ability to commit is going to necessarily go down when it has one or more permanent migrant members. This is not true if it has temporary migrants, because if it has temporary migrants, those people are going to be coming back all the time. So now you can punish those people when they come back 2 months later anyway. So the point is that when they go permanently, that is when these commitment problems will be most severe. What about the information problems? It's the same story there as well, right? Once the person has gone to the city, and if this household is being treated as the sort of, as a single unit by the network, then they always have an incentive to tell the network, well, guess what? He did really badly in the city this year. Then, their net income goes down, and therefore the transfers will flow in their direction. So this is a really serious incentive problem, the sort that you were bringing up earlier, right? They always have an incentive. In your case, I think what you had in mind was, effort, right? That what's the point of putting in effort, if I'm going to be giving money to the network when I have high income? Here the story is, you always have an incentive to report that this person whose income cannot be observed actually has lower income. And for that reason, of course, in equilibrium, people are not going to basically keep giving them transfers, and therefore the level of insurance that this household will receive is going to go down. Okay, so these are, I think, reasonably sort of, sensible reasons why the household will have, a household with migrants will have lower levels of insurance. But once we bring in this assumption about full risk sharing, it actually becomes much stronger than that. It has more bite, because when you have full risk sharing, either you're in or you're out. There's no option. There's no like partial risk sharing, right? I mean, this is it. So either now a household with migrants is either in the network or it is out of the network. And what we're going to assume is that the loss in commitment and the information problems together result in a situation in which a household with migrants basically is going to be excluded. So now you have two choices. And again, this is why the decision rule is going to be so much easier for us once we assume full risk sharing. Either you stay in the village, you have your rural income, your local income, and you benefit from the insurance network. Or you send one or more of your members to the city, you increase your income, but then you lose access to this consumption smoothing arrangement. You might have access to other things out there in the city too, right? Or this household itself might be able to go to the local moneylender and smooth out its consumption on the side. But we know that that's not going to be as good as what the insurance network was providing. Okay, so these are the choices that you have. Either you remain in the village and participate in the insurance network, or you send one or more of these people to the city and you add to your income, but you forego the services of the network. Okay? So now, given this sort of, these two extreme choices, this is what your decision rule looks like. Okay, and this is the keys. This is a very important expression because it really gives you a sense of what is going on over here. So this is the left-hand side is what you would get if you remained in the village. Okay, if I remember what I told you earlier, that your expected utility from consumption is just, it depends on the mean consumption and it depends on what we call the normalized risk, this risk term. MI is your mean consumption with insurance. And what this expression is, of course, is going to depend not just on your own income, but on the income of all the other people, on the income sharing rule, and I'm going to derive that for you momentarily. Okay, this is going to be derived endogenously, in the model, right? VI is a variance of consumption. And intuitively, when you're part of this insurance network, the variance of consumption is going to be low. It's certainly going to be lower than the variance of your income, right? That's the whole point of being part of it. Now, what happens if you send someone to the city? Okay, if you send someone to the city, then the household's income increases by an amount epsilon tilde. This is in proportional terms. Okay, so you can see here how these assumptions are getting built in, right? So what you're implicitly assuming is that this epsilon, this gain from migration is independent of your rural income, MA. You might not believe that. You might think, in fact, that households that are wealthier, in the rural area, they are wealthier for a reason, maybe because their members have higher education. It could be. If that is true, then in fact this assumption will not be valid. And when we get to the empirical work, we're going to actually relax this assumption. But for now, we're going to assume that basically all households increase their income by an amount epsilon tilde by sending their members to the city. Okay? Now, given that we have log preferences, of course, this term goes out separately on the right-hand side. And what we're going to assume here, which is a very important assumption, is that this epsilon cannot be observed. Okay? So every household gets this realization. It's private information. Okay? And that determines its decision whether it wants to stay or whether it wants to leave. So households are going to be sorting on this epsilon. Now, if they actually do send someone to the city, they increase their income in utility terms by this epsilon. But what happens to their risk? Well, their risk is going to change now, right? Because they're no longer part of this insurance arrangement. So in the extreme case, imagine that the household had no access to no other sources of consumption smoothing. Do you expect that the risk, the normalized risk that the household faced would be higher or lower than what it would have if it had remained in the village and was in autarky? So it had access. Suppose, for example, think of two situations. One is where the household is in the village and basically it has access to no consumption smoothing arrangements. It's going to face a certain amount of risk. That risk is going to be simply VA divided by MA squared, right? That's the risk it faces. Now when the household goes to the city, let's assume to begin with, there is access to no other sources of consumption smoothing. This is now the risk that the household is going to face. It's multiplied by this parameter beta, which we call the risk parameter. Do you think that beta is going to be larger or smaller than 1? Intuitively, what do you think is going to happen? Smaller. And this is there's a whole literature and migrations. You want to keep track of all of these things. That's what I've been trying to do as we go along, is to make sure that we keep track of the existing literature. So there's a whole literature which talks about how households will actually send someone to the city as a way of actually smoothing out their risk. You diversify your income, and therefore you reduce the income risk that you are facing. And so the idea is that even if you had access to nothing else, you would expect beta to be less than 1. Now, if you got access to some kind of government safety net or private credit or something like that in the city, then of course beta would go down even further. Yeah.
So if income's all independent within the village anyway,
yeah.
then why? So under that assumption, why does sending someone away change anything?
Because that's going to depend on your correlation between your income in the village and his income in the city.
You said they were all independent anyway. So if they were all independent in the village.
Maybe not across.
Not across. This is not village, and this guy's not gone to the village. He's gone to the city. So usually, what people assume is that when you send someone to the city, then because there is some kind of risk.
Yeah, because that's normally like, so we're in the same household, so we have some correlation in our income. I moved to the city, now there's a lower correlation in our income. If we assumed that when we were both in the same household, we had independent.
No, I never assumed that. In the household is one income.
Okay.
I never assume that. I'm assuming across household. Yeah. Exactly. So what you're going to do is diversify to some extent, right? So this is this is just building in this idea that there's a whole literature on this, by the way, and the classic paper is Lucas and Stark, for those of you in the JPE, like 1985 or something, and that's the one that brought up this idea of using these remittances as a way. So in our model, all of that stuff, the remittances and stuff, it's all there, it's all built in, and we're allowing for the possibility that this beta is less than 1. But the key assumption here is that this term here, what we're going to call the normalized risk, is smaller, in fact much smaller than this term over here. So even if beta is less than 1, this term can still be a lot smaller than this if in fact you have really good consumption smoothing in the network. And if that is the case, then basically if this gain, if in some sense the loss in sort of the insurance is sufficiently large, then you're going to need a big epsilon to want you to be willing to move to the city. And you think of the epsilon as in some sense the wage gap. Right? So intuitively, this inequality just pretty much tells you what the intuition is of the model. Now you've got to actually solve this whole thing out, right? And that's not going to be easy, as I'll show you. But you can see right away, just with this decision rule, what the intuition is over here and what is going on. The loss of this person is that their risk is going to go up substantially if they leave the village, send someone off to the city. And they'll trade that against the gain in income that this person will get by moving. Okay, is this clear to all? Yeah.
So is the epsilon private information?
Yes.
Yeah, but the gap is known. Right?
No. So that's the whole point. That the gap that we see is, think of that as sort of the average gap. So everyone knows on average, what this gap is going to be. But there's going to be what I'm going to do is I'm going to give you a distribution of epsilons. And then what you're going to find is what is the threshold epsilon above which people are going to want to leave. And so what you observe in the data is in some sense the average epsilon above that threshold is what you're actually observing in the data. You see what I'm saying? Okay. So we're going to get to that literally in 1 second. Okay? All right. So remember now what we have is full risk sharing. We have log preferences. So if you think back to the stuff that I showed you in the last lecture, basically what that means is that each household is going to be getting some fixed fraction of the total income that's generated in each state of the world, right? If you have an equal, if everyone has the same income, remember the epsilon is private information, right? So in terms of the observed income, everyone has the same rural income, which is MA. So then what would be the sharing rule that you think would be the natural one? It would be an equal sharing rule. So each one, if there are n people in the arrangement, you would get 1 over n. That's what you're going to get, right? So this allows us to actually write down what the mean and the variance of consumption is with insurance. Remember I told you this is going to be derived endogenously in the model, right? So it's really very simple. Basically, what is the mean consumption? It's the expectation across all states S of 1 over n of the total income that's being generated. So when you take the expectation, guess what? You end up with MA. This is not a surprise because there's no redistribution, right? Basically, all the money that goes in is being distributed. So on average, it must be that your consumption is the same as your income. And it's the same for everybody else in the arrangement. But what happens with the variance of consumption? And this is, in fact, the insight of this paper, in fact. This is right over here. The variance of consumption, when you write that down, is basically the variance of your income divided by n. And this is the part that this exposed risk-sharing literature completely ignores. This idea that when you have a larger network, you're going to have much less variance in your consumption. We're shutting down all this stuff about how much risk sharing you can have exposed because we're assuming that you have full risk sharing. But just because you have full risk sharing doesn't mean that you can actually smooth out your consumption very well. It really depends on n. So if n is really small, then you actually won't be able to smooth out your consumption at all. And I think I gave you guys the example right earlier, and I'll give it that to you again so you get the intuition for this. Suppose you have these two guys, back to the same example. You get 1,000 with probability 0.5, you get 2,000 probability 0.5. It's independent across the two of them. 1/4 of the time, they both get 1,000. 1/4 of the time, they both get 2,000. 1/4 of the time, one gets 1,000, the other gets 2,000, and vice versa. Now, if you had full risk sharing, what you would do is in half of the time, you would end up with 1,500. 1/4 of the time, you would have 1,000, and 1/4 of the time, you would have 2,000. So you're actually not smoothing out your consumption very much at all, but you're doing really well on risk sharing. And what this is picking up is the other side of it, that there is more to consumption smoothing than risk sharing. Yeah.
I know that you said you're not going to talk about topology, but in this case, topology of the network actually a lot, I guess. I don't know,
Are you thinking in terms of the correlation in the shocks?
Yeah, and also let's say that with different topologies, the impact on the variance of income wouldn't be so substantial.
So there will be something for you to get into, absolutely. So you can think, certainly one way to think about this is that we're assuming here, of course, that these incomes are all uncorrelated. Now, once they become, more like negatively correlated or something, then of course you have more opportunities for this, risk sharing. All of that is sort of, again, also swept under the rug, right? But that might be also something that you could exploit. But in any case, this is the point, right? And as I told you earlier, the key thing here, the key assumption here is that RI, which is basically the risk, normalized risk with insurance, is less than beta RA. And if this gap is sufficiently large, then you're going to need a big epsilon to basically want you to send someone to the city. Now, what is the level of participation in this arrangement? Now my decision to participate or not, of course, depends on what other people are doing. Because the more people who are participating, the better off I am going to be, right? Because this is going to get smaller and smaller. So this is obviously a solution to a fixed point problem. So what we're going to do is to solve that out first. It's actually not that difficult to solve if we make some assumptions about the epsilon. But intuitively, how do you solve for this? Basically, there's going to be some threshold epsilon above which people are going to want to migrate to the city in equilibrium, and below which they're going to stay, right? So the way that you solve for the participation is to derive the threshold epsilon at which the participation condition, which I just showed you earlier, that an inequality basically holds with, is exactly satisfied. Okay? Now we got to sort of describe what this epsilon distribution is. We're going to assume that this is characterized by some function f of epsilon, right? Then it must be that there is this fixed point where f of epsilon I is going to be exactly equal to n over p. N over p, p is the population of the community. N over p is a fraction of people in the population who are going to be participating. And that's literally going to be exactly f of epsilon I. What is epsilon I? Epsilon I, if you just go back to that decision rule, tells you exactly what it is, right? If you just go, let me just take it back so that you don't get confused. here. So epsilon I, you just take this on the other side, and you take this on the other side, and you get the expression for epsilon I where this condition is just satisfied. That gives you the threshold epsilon. Okay? So this is what you have. This is your fixed point condition. And we define delta. This is again the notation. You should keep track of it because as I move forward, you might need to remember it. So delta M is just the log of Mi minus log of Ma. In our particular case, remember Mi is equal to Ma. So this is going to be 0. Delta R is this expression over here, which is basically what's driving everything, right? Which we think is very large. As n gets bigger, what happens to Ri? If you remember, Ri is Vi, the variance, divided by the mean squared. So as n gets bigger, the variance gets smaller. So this Ri term gets smaller. So delta R is an increasing function of n. So the left-hand side is a linear function of n. The right-hand side is an increasing function of n. And what we want is to see whether we can, what are the conditions under which you're going to get a unique fixed point. So we make 3 assumptions here. The first is that the left support of the epsilon distribution is 0. The right support is unbounded. And the density F is decreasing in epsilon. This is just saying that better opportunities occur less frequently in the population. Okay? So given these 3 assumptions, you can show that in fact there is a unique fixed point. What this first assumption implies is that this F function here is always going to be greater than 0. The second assumption says that this F function is always going to be less than 1. Now this left-hand side is starting at 0 and is going all the way up to 1, right? So this F function is starting above, and it is, so the right side is starting above the left-hand side, and then it's ending up below it, right? So this is what it looks like. This is, graphically, this is what it is. So this F function, because of assumption A1, is starting above the left-hand side. And then by the time you get to P, it's gone below 1, whereas that line has reached 1. So you know that it's definitely going to cut it at least once. The third assumption ensures that this F function is strictly concave. Okay, now you might say, but this is just cheating. You just set it up to give you this unique fixed point, right? But later on when we do the structural estimation, and again, this is where you want to keep the theory and the empirical work tight, we're going to make the same, we're going to pick a distribution that actually satisfies each of those assumptions. Okay, so there is this consistency. But all this is saying is that with the simplest case where there's no heterogeneity, what we can do is to solve out for the level of participation equilibrium. Okay? Now this is not giving us any predictions for which households benefit more or less from the network, right? That we can actually test, because epsilon, we're going to assume is just private information. We don't observe it as the econometrician. All these households are exactly the same. So there's no prediction at all over here. To derive the prediction, we're going to do is to just extend this framework by allowing for households to have different levels of income, of rural income. Okay? We're going to introduce income heterogeneity. So what we're going to do now is to divide the community into k income classes of equal size. Okay? You go through the same steps as we did before, but earlier, of course, everyone was the same, and you could solve out very easily for Mi and Vi. Now, of course, it's a bit more complicated because you have these k income classes. But what we take advantage of, again, is this full risk sharing and the log preferences. Given these 2 assumptions, what I told you earlier, if you remember the general rule with full risk sharing is that the ratio of marginal utilities should be constant in all states of nature. With log preference, it's saying that the ratio of consumption should be the same. So this is just saying that C of some income class K in state S divided by the consumption of the highest income class K in state S should be some constant, let's call it lambda K. So we're normalizing here, so the lambda of the highest income class is going to be equal to 1. Okay? Given this, you can go back in and go through the same exercise to solve out for the mean and the variance of consumption. And it has a similar structure as we had earlier, but of course it's more complicated now. This first term here is basically the weight, the fraction of the total income that's generated in every state that goes to someone from income class K. So if lambda is large, for example, you get a larger fraction. What this is going to be determined in the model endogenously. Okay, so now that we have different incomes, we have different income classes, we're going to have to solve for both the level of participation as well as for the income sharing rule. There are 2 things. Okay? So lambda will be endogenously solved in the model, and the n's will be endogenously solved in the model as well. Okay? And you have a corresponding expression for the variance of consumption. Using the same approach that we had earlier, right? We just write down the variance of consumption. Remember, there's a particular sharing rule, but now it's not an equal sharing rule. It's not just 1 over n. You got to write this thing down. And then you go through the same thing, and you end up with this expression over here. Okay? The risk term, which is just the ratio, remember it's the variance divided by the mean squared. If you look at these two, it's basically this thing here and this thing here will cancel out. So your risk term is a function of the variance of income and the mean income in each income class. So it's a bit complicated, but it's independent of the income sharing rule, the lambdas. And it is the same for all income classes. Okay? So what we've got now is the mean and the variance of consumption as well as the risk term. Now you can go back to that decision rule and you can solve out, right? And so for each income class now, what you're going to get is a fixed point condition. You guys are looking quiet. Is it okay or are you not? Are you completely lost? Lost? No? Okay.
What assumption do you have to make? So if I thought about this again, what assumption would I have to make in terms of equilibrium so that the households who are in risk sharing don't benefit enough from wanting, you know, I say ex ante, oh, I don't want you guys to be in if you send a migrant away. But then I know that if I actually add you to this, so it's just
right, but the problem is you can't, because the epsilon is private information, there's nothing you can do. This is literally the best that they can do. So this is not behavioral or anything. You know, this is literally is the, you know, the equilibrium, right? There's nothing else that you can do. Now you go through the same steps, but now of course you've got an epsilon ik. So every income class is going to have a threshold epsilon above which people are going to leave, and that is going to satisfy this particular condition. Okay, so you're going to have k of these equations, and delta mk now is just the same notation as before. It's the difference between between your mean consumption and your mean income. So earlier, of course, this term was 0. Now, of course, it depends. If, for example, you could end up consuming more than what you earn on average, if in fact the redistribution favors you. So you can imagine a world in which, you know, the rich basically support the poor, so the poor end up actually consuming more on average than they actually earn. In that case, delta M for the poorer income classes would be actually positive and would be negative for the higher income classes. Okay? And then, of course, you've got your delta R term over there. Now, if we knew the lambdas, remember these terms here, these MIK and RI, these are functions of the n's and the lambdas. If we knew the lambdas, then you're done. Basically, you would have a system of k equations, and you would have k unknowns, which are the n's, and you would solve for participation. Just as we did earlier in the case without heterogeneity, income heterogeneity, we had just one fixed point condition which we could solve for. Now you would have k of them, but that's fine, but nothing else. It wouldn't be a problem. The problem, though, is, of course, you don't know what these lambdas are, right? And that has to be solved out. For that, you need one more condition. And where does that condition come from? You've got to make some assumption about what this community actually wants from this insurance arrangement. And what we're going to assume is that this community actually wants to maximize the surplus that is generated by the insurance network. Okay? So what is the surplus that is generated by the insurance network? So does someone have a question? No? Okay. So what is the surplus that is generated by the insurance network? Okay, so this you're going to sum over all k income classes. Okay, and what you're going to get is, for each person who's in the insurance network, you're going to get their expected utility from being in the network minus the expected utility that they would have had if this network didn't exist. For the people above the threshold epsilon ik, it doesn't even matter because they would have been outside of the network anyway, with or without the insurance arrangement. It wouldn't make a difference. They would have migrated in any case. So you only have to worry about people up to this epsilon threshold. Now, what is the insurance? What is the expected utility from consumption for them with insurance? Well, there's just this expression over here. It's log of MIK minus half of RI. Right? This is what we had earlier. And what is it that they would have gotten if, in fact, there was no insurance arrangement in place? They would have been on their own. Now, if beta is less than 1, as we think it is, then, of course, they would always want to migrate if they did not have an insurance arrangement, because, in fact, their risk is going down by sending someone to the city, plus epsilon is positive. So for sure, they would want to migrate, and so therefore, everyone is going to be sending someone to the city, and this is what they would be getting. Okay? And you integrate over all the epsilon. This is the density. and you go through the whole thing. And remember here, we're assuming that the epsilon distribution is the same for all income classes. And this is therefore the expression that you get for the surplus, which you can then simplify to this expression over here. Okay? And now you're in business, because what you're going to do is to maximize this surplus subject to the fixed point conditions. Okay? And basically, you're going to solve for, so think about how this works. The way that this would work intuitively is it would say, okay, I'm going to pick a particular set of lambdas, right? An income sharing rule. So just for you all to understand, so imagine that there are 5 income classes. Oh shit. Fuck. Sorry. Does this ever work? Okay. Okay, so what you're going to do, so basically imagine that there was, that we let's just pick an income sharing rule. Okay, this is a set of lambdas, right? So the highest income class, that the lambda is going to be equal to 1, and then for the other 4, you're going to give them a particular set of lambdas, okay, whatever they are, right? Remember, what is lambda? That's just a ratio of consumption between that income class and the consumption in the highest income class in each state of nature, right, which is a constant. So once we've picked the lambdas, then what we have to do is we say, okay, now if we know the lambdas, we can go back to those fixed point conditions, right? We know what those are. Sorry. You go back to this fixed point condition, and remember that these things here are all functions of lambda and n, right? So if you know what lambda is, then you can stick these things in here. You have closed form solutions for m, I, k, and ri. You stick these in here, and you solve out for the n's. Once you've got the n's, then you go back here, and you can actually figure out what the surplus is, because you know what the epsilon ik is. It's the threshold, which is just basically once you know what the n is, the participation is, you know what this threshold is, since you know this f function, and you know what these n's are, and so you just solve out for this whole thing, and you get a particular surplus. Then you pick a different set of lambdas, and you go through the same process. You basically search over all the lambdas until you find the lambdas, the set of lambdas at which the surplus is going to be maximized. Okay? That would give you the lambdas, it would give you the participation as well. Okay? So this is basically giving you the structure of the model. And I realize that this has gone a little bit quick for you, and maybe after the first hour you were not expecting this. But that's the whole point, right? So is that you want to start with the background, with the setup, but then you want to do the serious economics as well, right? You don't want to just fluff around. So this is the setup that we have. And now what we can do is to use this setup for 2 things. We can now derive predictions about which households will actually benefit more or less from this insurance arrangement. And we can also use this setup to actually estimate the model and do counterfactual simulation. So we can do both. We can do reduced form estimation, and we can do structural estimation at the same time with this framework. Yeah.
So it seems like it's quite crucial for F the distribution have to be the same across income categories. Do you have a sense of whether
it doesn't have to. This is a very good point. So in terms of actually getting the analytical results, it does. But when we do the structural estimation, I will relax all of those things. So this is again, when I get to them, you'll see this as when I get to the empirical work, I will keep trying to relax different assumptions. The point is when you do the analytical stuff, you really want to set things. If I didn't do that, I probably wouldn't get any analytical results at all, because then I can explain anything. If the epsilon distributions are different across different income classes, I cannot ever make any predictions about migration rates, for example, across income classes, because that could be all explained by differences in the epsilon distribution. You see what I'm saying? So there's no point then. I mean, if you want to start off by getting some analytical predictions, you're going to have to necessarily make assumptions. There's no way around it.
I agree.
But once you've done that, what I would tell you is then you have to try to relax those assumptions when the time comes to actually do the testing.
But just to get a sense of how plausible this particular necessary assumption is,
Yeah.
Do you have a sense of whether there is a big difference in the number of households with temporary migrants across income categories?
No, I don't actually.
Because I might think that households with temporary migrant workers have a higher chance or a higher need for
Or because they have more contact. Right, and you might think that that will vary with.
If it's correlated with income class.
But the thing is, yeah, right. But the thing is that you're thinking about a world in which you're not off. A world in which, in fact, it's hard to find these opportunities at the destination, and the contact allows you to then build up and then have a permanent position. Whereas what we're thinking about here really is this world in which, in fact, there are no network stories or any other stories in the labor market at all in the destination. There's just heterogeneity in your opportunities.
So the way it's a bit weird, right? So you're taking into account how many people will stay in the network, but you're not taking into account how many people are going to be at your destination. The way it's a bit product.
I will do that in the empirical work. In the empirical work, I will even allow for the possibility that in fact some of these castes have established networks in the destination, and others have not. But as I keep saying, what I want to do in the theory section is to basically, I will make the assumptions that I need to make, so I can get analytical results. There's no point if I started to bring that in over here, then basically what you would do is you would just stop and say, you know what? And I hear this all the time. I really don't have any analytical results. I'm just going to go and estimate the model. And that's fine. As far as I'm concerned, then you cannot get any reduced form implications from that. You cannot look in the data in a way that gives you some confidence that you actually have something there. Then you can go and do your structural estimation and put in all the complexity that you think is relevant, empirically in a particular setting. Right? That would be my view of how I would want to do it. But as you can see, as we're doing this, you can see what the cost is. I have to be making assumptions. If I didn't make the assumption that the epsilon distribution was the same across income classes, I can make no predictions at all about differences in migration across income classes based on anything else. Because that can always explain everything. Right? That's clear. Okay. So this is the setup that we have. So now what we're going to do is actually now to derive some predictions, as I said. So that's the first thing we're going to do, is to derive some reduced form predictions, which we can test. What we want to see is which households actually benefit more or less from this network, given the structure that we have, and can we then see whether in fact it's those households which have more or less migrants, right? So if you look back at this surplus function, it's actually very obvious where this is going. If you look at this surplus function over here, if you fix the participation, then look at this term over here, right? So suppose you fix the level of participation in each income class, this epsilon, this threshold. Okay, you fix that. Then you would surely be able to actually increase the total surplus that is generated by taking $1 from the relatively high income classes and giving it to the low income classes, given diminishing marginal utility. Remember, you have log preferences here, right? So if I take $1 from the high guys and give it to the low guys, then of course the total is going to increase. And if I don't change the participation, then for sure that's going to increase my surplus. Remember, Ri is independent, as I showed you, of the income sharing rule. So that's not going to change. The amount of risk sharing is going to be exactly the same because the number of participants will not have changed. And everything is the same. It's independent of the risk sharing rule. So for sure you can increase the surplus by redistributing. But what is the consequence of that? If you relax the assumption that participation is fixed. Suppose I took $1 from the rich and gave it to the poor. What would happen to the thresholds, these epsilons? What would happen to the threshold epsilon for the poor, for example? Would it go up or would it go down? Now that you guys have been so quiet, let me now push you guys. What happens to your threshold epsilon when I take $1 from the rich and give it to the poor?
It comes down because those households get less benefit of staying in the network, so the cost of going away is kind of lower than it was before.
For the rich guys, not the poor guys. The poor guys, it goes the other way because now the poor guys are actually better off, so their epsilon is going to go up. So what's going to happen is that the epsilon is going to go up for the poor guys and it's going to go down for the rich guys, the threshold epsilon. And the effect, of course, now on participation is going to be ambiguous. You don't know which way it goes. So in fact, this is a really hard problem to solve. And we cannot actually derive the income sharing rule analytically, a closed form solution. So the trick that we use actually is to focus on, so remember the income sharing rule, think about the case, a simple case, but there are just two income classes, a high and a low income class. And let's, to make life simple, going on with your story, let's assume that the epsilon distribution is the same for both of them. And let's assume that the risk, this RA, is also the same for both of them. So left to themselves, these two income classes would have the same level of migration in autarky. Okay? If you had a sharing rule where you in fact gave each income class exactly the amount of consumption that it had as its income, the average consumption equal to the average income, then you would have the same level of migration as well for the two income classes. The epsilons would be exactly the same, right? But of course you might ask yourself, okay, is that really the optimal sharing rule? you might think that you might want to actually increase that. Now, if you increase it from that particular point where there is no redistribution at all, where the poor guys are consuming on average exactly what they are earning, and the rich guys are consuming exactly what they are earning as well, and suppose I just redistribute it slightly, what would happen? Well, the first order effect, of course, would be this direct effect, which is that you would basically increase the surplus because of the redistribution, because of diminishing marginal utility. But what we show in the paper is that the indirect effect on participation will actually reinforce that effect. The total number of poor guys who stay exceeds the total number of rich guys who leave. And so, in fact, your risk sharing will actually go up at the margin, just at the margin. We can't show you how much redistribution there will be, but there will always be some amount of redistribution. Now, that is a really difficult problem to solve analytically. But we can actually solve it for that one special case. And so what that means is that you will always have some redistribution. So if you continue with this assumption that the risk is the same for both income classes and the epsilon distribution is the same for both income classes, if you have this redistribution, then it must be that relatively wealthy guys in their caste are going to benefit less from the insurance arrangement and therefore will be more likely to have migrant members. Okay? So that is the first assumption that we have in the theory. Okay? That some redistribution is socially optimal, which implies that relatively wealthy households in the community should be more likely to have migrant members. Okay? Now we go to a second prediction, which has to do with the income risk that the household faces, RA. Okay? So intuitively, what happens when a household faces more income risk? Is it going to be more or less likely? What is this epsilon threshold going to be? Is it going to be higher or lower? Can you tell me?
It's on your side.
Oops, is it?
Okay.
Yeah, so what happens to epsilon threshold though? The epsilon threshold is obviously going to go up, right? Obviously. And the reason is because Ri is the same. Remember, it doesn't depend on anything. Everybody is facing the same risk in the insurance arrangement. But when they leave, when they send someone to the city, now their risk depends on their own income. And if in fact there's a group of households which have higher income risk than another group of households, those guys are going to be benefiting more from the network in some sense, and therefore they'll have more to lose by sending someone to the city. Now again, this is not an easy problem to solve because of this stupid thing about redistribution. It turns out that when this happens, you're going to have more of these guys sitting around who are benefiting from the network. So there'll be more risky households in equilibrium than safe households in the network. And so now there's this potential to actually redistribute by taking a dollar from a large number of risky guys and giving it to a small number of safe guys. But again, we worked through this in the paper, and what we can show once again is this one result for sure, which is that everything else equal, households that face greater rural income risk are less likely to have migrant members. Now you think about the standard story. Suppose, in fact, I didn't tell you any of this stuff, and you just have to start from scratch. And I told you that there's a household in the village that is facing more risk. Is it going to be more or less likely to have migrant members? What would your first response have been? The other way around. Because the more risk it faces in the village, the more likely it would actually send someone there to diversify. And the point is that there's nothing inconsistent with our story. Remember, we are allowing beta to be less than 1. So it is very possible that by sending someone to the city, you actually do reduce the variance, the risk, the income risk that you face. But the point is that that's not relevant. What really matters also is the fact that you're going to be losing this consumption network. And as long as beta RA is larger for you, you're going to be less likely to send someone to the city. And so in that sense, this is a very strong prediction because it really separates our story from alternative explanations, as you will see. Okay? So now that we have this, let's actually look at the data. Okay? So remember, there are 3 testable predictions from our theory. The first is that income is redistributed in favor of poor households within the caste. An implication of this, or a corollary of this, is that relatively wealthy households who benefit less from the network should be more likely to have migrant members. And the third is that households facing greater rural income risk who benefit more from the network should be less likely to have migrant members. Okay, and I'm going to basically test each of these things, and at the end I'm going to also show you some additional tests which validate the key assumption that permanent male migration is associated with a loss in network services. Okay, so this is going to be the roadmap for the empirical work. So you can see the structure here. We started off with these stylized facts with this big macro thing, right? India versus China. Then we kind of gave you some descriptive evidence. Then we have a model with some predictions. And by the way, we can also estimate this model because we have all the equations that we need. We have we have closed form solutions for the mean and the variance of consumption. We have the fixed point conditions, and we have the surplus. We can take all of that together and estimate the models of this, all the parameters of this model, right? And we will do that later. Okay. So now let's talk about alternative explanation. This is a good time to do that. So one alternative explanation, which is based in fact on my own work, so in a way there's, I don't want to rule this out at all, is in fact the strategies that we talked about, where in fact these castes actually send groups of their members to the city. So imagine that this is a strategy that all these castes are using. They realize that if an individual goes, you have all these information and commitment problems. It can't work that way. So we'll only send people when we get a large enough common shock, which allows a bunch of these people to move together to the city. Now imagine now a world in which there are a few castes which are lucky to get those common shocks, and they set up their networks in the city. And any member of those castes can move easily. And then there's a whole bunch of castes which are basically shut out. So what happens to your urban labor market now? It's not a competitive market anymore, right? I mean, this is a very heavily, there's a lot of monopoly power in this market. Those people who belong to those lucky castes are going to get rents in the city. So you're going to have wages which are too high in some sense. And that's going to explain the urban-rural wage gap. It's not based on the imperfection that we're talking about in the insurance market. It's based on an imperfection in the labor market. And that's what's generating this thing. And you will not have movement to the city to close that, because if you go on your own, you can't actually enter into the labor market, right? You need to be, it's like a closed shop. Unless you're a member of one of those networks, you can't get in. So this can explain both the low migration and the large wage gaps.
Why don't people who are members of that caste move in?
What's that?
Why don't people who are members of those castes move
No,
in?
we would assume that they would move, but the point is that that's still going to be the pool is going to be very restricted, right? That would be our story. And then, of course, you have alternative explanations for redistribution and increased exit by relatively wealthy households. But the point is that none of these stories will explain, in particular, the third prediction, which is that households that face greater rural income risk should be less likely to have migrant members. There's nothing here which tells you about that, right? And that's the key prediction, I think, which allows us to separate our story from these alternative explanations.
Do you have a sense of how other characteristics of the household are correlated with the risk they face? So
I don't. That's a good question, and I don't know the answer. I know what characteristics determine their income, their average income, but I don't know what determines their risk, because we never needed to use it. But it's a good question. I mean, we should know that.
You have information on their income sources?
We have information about the income sources, not quite in the data that I'm going to be using. What we have is information about the household characteristics. So we will have the number of earners, we'll have education, we'll have land value, but we will not have it broken down in the way. ICRISAT does have that, but not the data that I'm going to be using. You'll see. Okay? All right. So this is basically saying, okay, these are the alternative explanations. We can pretty much rule these out. Now let's go ahead and actually test this. So how do we actually start? Let's start off with the redistribution. So how do you actually test for redistribution within these castes, which is the first prediction? So remember, Townsend was using these ICRISAT data, which is data over time. And that's the one data set that I know, in India at least, which will have data at the caste level, and it's data over time for a bunch of households. Now the big limitation of the ICRISAT data is that it's only 6 villages, and it's a very small number of castes. There are only 7 castes. So there's only so much that you can do with it. Okay? But we can use that. We have income over 7 years. This is the new panel, the more recent panel from 2005 to 2011. And there's also consumption data over 4 years. But as I said, this is very limited. And so what we do is to use the REDS data, which I used earlier to show you those results on the caste loans and stuff. That was from 1982 and 1999. Now in the last round of the REDS in 2006, what they did is in the census, which they do before they do the detailed household survey, they actually collected information on permanent migration. So for each household in the census, they asked them whether there was a member of that household who had permanently moved out of the village in the past 5 years. Okay? So the problem with the REDS, and this is great, right? Because this is over, a whole bunch of states, and is, there are many, many castes, and so it's, much better data for us. The big problem with this data is that it's actually a census, and they ask about the income in the year preceding the survey round. But whereas what we want for the theory is not just 1 year. What we want is your average income over time. We want the variance of your income over time as well. And so what we do is to actually impute the average income and the variance of income using the ICRISAT data. So it turns out that the ICRISAT data and the REDS data have many, many variables in common. So you have information about land holdings, soil quality, irrigation. We have information about the number of household, adult workers. We have information about education. And so what we do is we basically run a regression with ICRISAT data where we regress the average income of the household on a bunch of these household characteristics, and we interact that with mean village rainfall. Okay? Once you estimate that relationship, that equation, we take those estimated coefficients, use the same variables in the REDS data to actually predict what the average income would be for one of the REDS households. We do the same thing for the variance of income as well. Okay? And this is what we're going to be using for much of the analysis, but not all of the analysis. For some of it, we'll be using the straight income, as I'll show you once we instrument. But for much of it, that's what we'll be doing. Okay? So this is now just looking at the income and the consumption of the ICRISAT households. So what we do here is we take each caste and you break it up into 5 income classes. Okay? And within each income class, what we do is we get the average income, and we take the ratio of that to the average income in the highest income class. So by construction, this ratio is going to be 1 in the highest income class. So what you're seeing here is that the lowest income class is earning about 12% of the highest income class. Okay? In column 2, we do the same thing with consumption. And what you see over here is basically that this ratio here is much larger than this ratio over here. Okay? This is telling you that something is going on here. There is some kind of redistribution. The ratio of income is much smaller than the ratio of consumption. Okay? We go to the REDS data and we go through the same exercise. The numbers are not exactly the same, but you get the same pattern. Once again, the ratio of consumption is much higher than the ratio of income in the lower income classes. Yes?
Excuse me, and the income classes, we adapt in a single shot of time, or this is averaged over some period of time?
So remember here, by now, there's no time dimension to this because what we're taking is the average income over time, but we're taking that, we're just regressing that on fixed household characteristics. So there's no time dimension to this, right? It's just literally the average income. It's a cross section.
Okay, so.
But that is what we want, right? Because remember, that's what the theory is about, right? The theory is not about changes over time. You're making a one-time decision whether you want to participate or not, right?
How come they're all more than 1, the consumption income ratio? Shouldn't somebody be less?
Well, these guys are always going to be 1 by construction, right? It's a little bit confusing because it's the ratio of the ratios.
Oh, it's weird, okay.
That's right. So don't get into that. So I know that this is confusing for that reason, but it's the ratio of the ratios. Okay. And then the other thing I want to show you, one other thing. So this is basically just giving some descriptive evidence that there is redistribution. And by the way, this is if you look over here, if you look at the relative consumption here, this is an extremely high level of redistribution. So let me tell you a story here, which as I said, I don't want you to think I'm stupider than I am, but when you do the structural estimate, if you look at the model, all you need actually is the mean and the variance of income. You don't need consumption at all in the model, right? The model actually spits out for you the lambdas, which is the relative consumption with log preferences. So when we did when we were writing the paper, we did the structural estimation, and we only constructed the mean and the variance of income. And we got those lambdas, and those lambdas were like really high. And so we were like, hang on a second, this is a really high level of redistribution. What is going on within these castes? And then we actually thought, well, let's just construct the consumption the same way using the ICRISAT data, and let's see what it looks like. And it turned out, in fact, that it was high here as well. So if you look at this is an extremely high level of redistribution. Okay, I mean, the extreme would be 1, obviously, right? But they all have equal, consumption. And this is despite the fact that their incomes are much lower over here than these guys. Okay. Now, apart from the redistribution, we can also look just descriptively at the other prediction of the model, which is that as you basically redistribute, the relatively poor households are going to be less likely to have migrants, and the relatively rich households are going to be more likely to have migrants. And that's what you see over here. This is not monotonic, and it's not like crystal clear. It's not a very sharp pattern, but clearly these guys here have lower migration. It's about 3% versus these guys over here who have about 5%. I'll do a much better job of matching this later on when you do the structural estimation, okay? Trust me. But this is giving you at least some evidence without any conditioning or any anything else that there is some relationship here between your income class and the level of migration. Of course, the problem here is that relative income, remember these are relative income classes, will be also correlated with absolute income. A household that has higher income on average is going to be in a higher income class. Now we have 100 castes over here, so it's not a perfect correlation, but it's certainly going to be a positive correlation. And we might think, now this is the time to relax these assumptions of the model. We might think, for example, that higher income households have better opportunities in the city. The epsilon is different for them. Or it might be that if you're a higher income household, you just have the money or whatever it is to actually move to the city. Or, for example, you might have more education and therefore you're going to do better in the city. So for all of those reasons, we actually want to control for the household's own income to actually test the predictions of the model about how its relative position within the caste should matter.
How do you explain the fact that not only do you have a substantial reduction in the gap between the classes, but also you homogenize the class a lot in terms of relative consumption? If I look at relative consumption of rents, then basically the first four don't differ between them, right? Because that's very
Well, they do differ. You think they're quite close, though.
yeah, but they're incredibly close. How do you justify that not only you reduce the gap?
So here's a problem. So this is the thing with this kind of thing. I mean, what I'm going to do is, as I said, when we estimate the model structurally, you're going to see that this is exactly what it's going to generate. The model will generate that. And at that point, I will give you an explanation for where this is coming from. There's two explanations for this. One is in fact the story that we're telling, which is that in fact they're trying to maximize the surplus function, and because of diminishing marginal utility, you want to redistribute. The other story is that in fact, you know what, there's some notion of fairness in here. And in fact, the surplus function that we wrote down is the wrong function. And in fact, you're putting in fact more weight on those lower income classes. Now, right now, we can't say anything about that, but we're going to get, when we get to the, to the structural estimation, we'll be able to say something about that as well. Okay? Okay, so now let's test the reduced form predictions, right? So remember, the first prediction was that relatively wealthy households are more likely to have migrant members. Now, with a single community, you cannot distinguish between relative and absolute wealth, right? There's just one community. And so in the theory, we didn't have anything to say about that. Now we have 100 castes. So we can control for the household's own wealth and see whether, conditional on your own wealth, if you happen to belong to, let us say, a wealthier caste, you are going to be less likely to have migrant members. Okay, so that's the first thing that we can do, and this is the basic specification. On the left-hand side, you have this indicator whether you have any permanent migrant members. On the right-hand side, you have the household's own average income, and this is the average income in its caste. Okay, and in addition, we can stick in one more regressor later on, which is the risk, the income risk that the household faces, which allows us to test proposition 2. And what we expect is that those households which face more income risk should be less likely to have migrant members. Okay? So we're just using the same data. This is the data from the census from 2006. And the first specification is just testing proposition 1 on its own. So what the theory says is that conditional on caste income, as the household income goes up, is relatively wealthy. It's basically subsidizing the other people, and therefore should be more likely to have migrant members. But we have other reasons why we might think that household wealth is going to have a direct effect. It could be because the epsilon distribution is different for them. It could be because they are less risk averse. Who knows, whatever it is. So we don't want to really interpret this coefficient here. What we really care about more is the coefficient on the caste income. So conditional on the household's own income, as caste income goes up, it's going to be less wealthy, relatively. It's going to get subsidies, and therefore should be less likely to have migrant members because it benefits more from the network. And that is precisely what you see. This coefficient here is negative and significant. In column 2, we add in the income risk that's faced by the household. Okay, and consistent with proposition 2, you can see that this is also negative and significant. Now, we have, of course, set the whole story in terms of this caste as the unit around which these mutual insurance arrangements are organized. But there's, as I said, a whole literature. Like you look at Townsend's paper, it's all about the village, right? But that's, of course, for convenience reasons because the ICRISAT data is at the village level. He didn't know any better, and so he used the village. Someone might say, well, how do you know that it's really the caste and not the village? So what we do here is to put in not just the caste income, but we also put in the village income. And guess what? This is small. It's got, not the right sign, and it's totally insignificant. What we do in column 4, forget about column 4. We go in column 5 is we actually put in we put in the caste income within the village. And this tests this idea that is it really the full caste network which extends over many villages, or is it really just the guys from your caste who are inside your own village who really matter? And again, you see the same result. This is really small and insignificant, and the other coefficients remain just the same. Okay, so this is giving us, and what's nice about this is, I guess I should have mentioned this, when we derived proposition 1, what we assumed was that the epsilon distribution was the same across all income classes, and that the risk, the income risk, was the same across all income classes, right? What we're doing here is we're controlling for that by putting in the household income. When we derived proposition 2, which is about the income risk, we assume that the mean income was the same across all risk classes. So in a sense, when you run this regression, you're conditioning correctly for both of these things. And so you're in some sense, you're testing this theory as you should with the correct controls, with the correct conditioning. And you still get the same patterns over here. And as I said, there's this last result here, this negative thing on the income risk, to me is really, really striking. Because your instinctive response would be that, look, it's facing more risk at home. Conditional on its own income, it must want to send people to the city to diversify. And you see exactly the opposite. Okay? So these are the reduced form results. Now what we're going to do is to actually estimate the parameters of the model and do counterfactual simulations. Okay? And you'll see that this is going to give us some additional support for the structure that we have. Okay? So there are basically two exogenous variables in the model. There's the mean income and there's the risk, right? Which is just the variance of income divided by the mean squared. And when you have multiple income classes, you're going to have that in each income class. Now in our data, of course, you don't have just one community, you've got 100 castes. So what we're going to do is within each caste, we're going to break it up into 5 income classes. We also tried with 4 and 6, it doesn't make a difference. We're going to break it up into 5 income classes. Okay, and within each caste, we're going to therefore have a mean income and the risk term. Okay, so there's going to be 500 of these income classes in the data where you do the structural estimation. So we're collapsing. So when we did the reduced form, you had 20,000 observations or something. Now we're going to collapse it up into 500 of these risk classes. Okay, so it's exactly in line, consistent with the theory, except that you're going to have now multiple communities, not just one community. But the estimation is going to be exactly as I showed you earlier. If you remember, you had closed form solutions for the mean and the variance of consumption. Then you had your fixed point conditions, and then you had your surplus. And that's all we're going to do. Okay, we're going to use those equations to actually estimate the model. Okay, so we're not just writing down some equations and estimating the parameters. We actually have a theory that we're going to use to actually estimate the model. Okay, so to understand how the structural estimation works, suppose to begin with that the beta parameter and the f function are known. And I told you this earlier at the time, right? So if you knew the lambda parameter, if you knew the income sharing rule, right? You knew all those lambda coefficients, or whatever they call the lambda, the income sharing rule, then you could basically go to the fixed point condition and solve for the participation, the ends. Once you have the participation in each income class, you can go to the surplus function and you can compute the surplus. Then you would you use a different income sharing rule and go through the same exercise. Remember, you're doing this within each caste, right? And you go through the same exercise and you basically find the income sharing rule which maximized your surplus. And if the model was correctly specified, then in fact at that particular point, your predicted migration and the actual migration should exactly coincide. Right? That would be, if you knew what the beta and the f function was. Now, suppose we don't know what the beta is. You could go through the same exercise again. You would do the same thing for pick up arbitrary beta. Go through the same step of finding, the set of lambdas that maximize the surplus. And then at that point, you would try to see whether the actual migration and the predicted migration coincided. Now, do you think that they would coincide? No, obviously not, because you've got the wrong beta. You just picked some arbitrary beta. But the point is that suppose, for example, your predicted migration was lower than the actual migration. Now you know what to do, right? Basically, what you would do then to increase your migration would be to reduce the beta. If you reduce the beta, your predicted migration is going to go up in every income class, in every caste. So there's a unique beta which is going to exactly match up the overall predicted migration and the actual migration. And that's exactly what we do to estimate the beta. Okay, that gives you an estimate of the beta. And where do you get the confidence intervals from? Remember here there are 100 cars. So we're going to jackknife the standard error. So what we do is we repeat this exercise, removing one cast at a time and repeating the exercise. So you get a distribution on the betas. Okay? So it's very simple, it's very intuitive, we're not putting any extra structure on it, this is all we're doing. Now there's only one thing that's missing over here, and that is the epsilon distribution, right? Where do we get the f function from? Okay, so let's talk about how we get the f function. Now if you remember, I made 3 assumptions when we were deriving the fixed point. Assumption 1 was that epsilon was bounded below at 0. Assumption 2 was that it was unbounded to the right? And assumption 3 was that the density was decreasing in epsilon. So it turns out that there's one distribution which satisfies each of those, and that is the exponential distribution. And what's nice about this is it has a single parameter to estimate as well. So what we're going to do is we're going to assume now that in fact the epsilon is distributed exponentially. Okay? So now the question is, how do we actually get this f function, right? What is this new? We basically need to estimate this new parameter. So the way that we do that is we basically do this out of sample. Okay? We're going to use the REDS and the NSS data that we had earlier to first of all compute the income gain from migration for households with migrants. So you remember here there's an epsilon threshold above which these households are going to migrate, right? Or send migrants. This is telling you that basically when you look in your NSS data at the gap in the wages between the rural and the urban, it's those households above the threshold who are giving you the data, right? So those are the households you want to look at. So basically what we do is we say, look, we look in our REDS data, in our census, we know that 4% of the households have migrant adult males. So we know that those households all must have had an epsilon draw above that threshold, right? And we're going to assume, in fact, that those households are in some sense representative. So in fact, they are at the 98th percentile of the epsilon distribution. Okay? Now the question is, for those guys at the 98th percent of the epsilon distribution, what is their epsilon? For that, what you need is the income gain from migration, right? And for that, what you do is we say, okay, I know from the data the land value of this household. I know the number of adult males, including the one who's migrated, obviously, I count that person as well. So I can actually compute, given the NSS wages, what the income of this household would have been if everyone had stayed in the village. Given the NSS wage in the city for that particular educational level of that particular household, you know what the wage would be, the increase in wage would be if one of these guys had moved to the city. And you can use that to actually compute what the income gain is going to be from migration, which is epsilon tilde. This is a percentage increase in income for these households with migrants. Now you know that those households, as I said, are at the 98th percentile. So in terms of this particular formula, this x is going to be basically 2. No, sorry, it's going to be 4. Right? And you know this epsilon hat, which is just going to be the log of 1 plus epsilon tilde, where you actually measure the epsilon tilde from the REDS and the NSS data. So what you get from all of this is basically an estimate of this new parameter. And so using only data on people who have actually migrated, who are above the threshold, to actually back out what this entire distribution of epsilons actually looks like. Now once you've got this, then you're done. Then you can go back and you can estimate the beta, just as I told you, because you know what that f function looks like and we know what the new parameter is. Okay, and that's what we do. Okay. So this is what it looks like. Okay, this is not easy for you to see, but in columns 1 and 2, what we do is we just show you what the actual data looks like, the actual measured data, right? So remember here we have 100 casts. We're going to break them up into 5 income classes. And then what we're doing is we're taking the average across all casts to give you the relative consumption for each income class, which I showed you earlier, by the way, right? And we're getting the migration in each income class as well. Okay, as I told you, the overall migration is 4.3%. It's really low, right? Now in columns 3 and 4, what we do is to report the predicted lambdas, which is nothing but the relative consumption. That's exactly what it is with log preferences, right? It's the ratio of consumption in each income class to the highest income class. This is exactly the same as this. It's the lambda, and this is the migration that's generated by the model. And what you find here, and this is getting to your question about how do we actually interpret, what is it that is, why do you have this high level of redistribution? The model is actually generating these lambdas that are really close to the actual consumption. And we're not doing anything here extra. We have just a single new parameter, we have a single beta parameter, we're assuming that you're just maximizing the total surplus, placing equal weight on all the income classes, and that's it. I've not dumped in, I've not put in extra parameters to make it fit better or anything. This is it, clean, nothing else. And what's remarkable is that this is within 5% of the actual consumption data. And remember, we're not using consumption data to actually estimate the model. We're only using income data. And you're still coming this close to the actual consumption. Okay? In fact, where you do worse, and remember, you're matching on overall migration. So you're going to get 4.3% here as well, just by construction, because you're matching on that moment, right? So of course, you're going to get that. But we actually do really badly on migration by income class. We start off like really low, much lower than the actual thing, and we end up much higher. So then this is where it's not cheating, but this is where you've got to now start to open it up, right? We're going to expand the parameter space, see whether we can do something. So the first thing we thought about was, okay, let's try to say play around with the new parameter. We've assumed now that everybody has the same epsilon distribution. Could it be, for example, that the epsilon distribution is different? It varies by absolute income class. It's not by relative income class. It's not where it could be that, depending on your absolute wealth, your wealth position, you just have a different, kind of opportunity in the city. And so what we do is we basically break up the REDS census into 5 income classes without regard to caste affiliation or anything. And then what we do is to compute the new parameter within each of those income classes. And then for every relative income class in our caste, we assign it to an absolute income class, and you pick up that particular new. Okay, so now instead of having just one new parameter, you've got 5 new parameters. Okay, so you've expanded a little bit. But guess what? If you look at columns 5 and 6, it really doesn't change at all. In columns 7 and 8, what we do is we say, well, maybe the story is about these caste networks in the city. And what we find in our data, in fact, is that there are some castes which have much higher levels of migration, and other castes have almost close to 0 migration. So it could be that, in fact, there are some castes which have just got a bunch of people in the city, and that is why they have higher levels of migration. And if you use the same formula that I showed you earlier, this formula over here, if this thing here is much larger, then of course nu is going to be smaller. Right? For the same epsilon hat, this nu will be smaller. Remember, nu is going to be is 1 divided by the expectation of epsilon. So it means that you're going to have basically effectively castes which have larger networks in the city are going to effectively give their members a higher gain from moving to the city. So when you do that, you estimate it separately within each caste, you still don't do anything. Now your beta parameter has gone below 1, which is kind of what we expected earlier a priori. But apart from that, in terms of a prediction of the migration, you're still doing crap. I mean, you're really not getting anything at all. And so the last thing we do is to actually free up the beta parameter. We allow the beta parameter to actually be a linear function of the mean income. The idea being that your income is going to determine the kind of risk-sharing arrangements that you have outside of the network. And when you do that, you do much better. Now you actually match up on the migration really beautifully. You even get this sort of non-monotonicity where it goes from the 3rd to the 4th, it goes down, and then it comes up. That's exactly what you have in the data as well. If you look over here, it's going down and then coming up. And you can even get that little dip over here, even though we're actually not, we're making beta a function of the absolute income, not the relative, income of the class within its caste or whatever. And you now, in the last specification, you do much better, but remember, you have only added on 1 more parameter. So you still have only 3 parameters. So you have a model with just 3 parameters, which is able to explain all of these things. And now there's a whole literature in migration, for example, which tries to match migration levels based on wages or income at the origin and the destination. And as you can imagine, especially with the cross-country regressions, it does a terrible job. So what do? They just stick in this thing called moving cost, which is basically a meaningless term which just picks up the residual. What we have here, in fact, is some structure on this moving cost. And this brings us to the migration literature. What we are claiming is in this particular context, the moving cost is actually being driven by this sort of risk-sharing arrangement and the loss of this risk-sharing arrangement. And with that structure, we can pretty much explain migration using the actual observed wage gaps and nothing else. Okay? Let us see how the counterfactual simulations look. And this gives you even more support for the story that we're telling. So what we're doing here is we're changing the 2 parameters. One is the new parameter. Remember, as new gets bigger, in fact, the income gap is getting smaller. Okay? It's the reverse of the 2. So by the time you get to this point over here, you've reduced the income gap, the wage gap, from about 20% to about 10%. But your migration hardly declines by about 1 percentage point. And the basic result, which you've seen with all these other things that I showed you, is that just like I showed you at the macro level, migration is just really unresponsive to the wage gap. People don't care. You could double the wage gap from 20% to 40%, and this would hardly increase from 4.3 to I think like 5% or 6% or something. But it hardly responds. But what about the beta parameter? If you change the beta parameter, if you reduce the beta parameter by 50%, which basically means you're halfway to, in some sense, full risk sharing, you would increase your migration from 4% with the flexible specification, which is the last one, to as much as 15%, to as much as 9%, which is about at 50%. Okay? So what you're seeing here is that where this is responsive, and we saw that with the reduced form as well, what migration seems to be responding to very much is this risk. And interestingly, it's the risk in the origin that it seems to be responding to. And why is that the case? It has to be because there's something that happens to these households when they migrate, which makes them that much more sensitive to their origin risk when they've moved to the city. And it must be because they're kind of losing something. Okay, how much time do I have? I still have some stuff to do, so 4 minutes? 5 minutes? Okay. Maximum, okay. I know, they're tired. Okay, so let me in 5 minutes try to give you a couple more things just to show you how you can complete a paper of this sort. So now you've seen big picture stuff, you've seen theory, you've seen reduced form, you've seen structural estimation. Now let's look at some instrumental variable regressions. Okay, now you can see all of everything you can ever want to do in one paper, right? So what we're doing here is to test the key assumption. Remember what's driving all of this is this assumption that if you actually, if you send someone to the city, you're going to lose the services of this network. Now we can't test that assumption directly, but what we can see is whether households with migrants have lower participation in this insurance network. Now to do that, we can't use the census data because it doesn't give you information about participation. You have to go back to the data from 1982 and 1999, which I showed you right at the beginning, when we were looking at these transactions within the caste, right? We're going to use that data. And now what you're going to have is, on the left-hand side, you could have migration, you could have participation in the network, and we can also use marriage because that's a good indicator of participation in the caste network, inter-caste marriage, right? Notice now that you have household I, and you also have a subscript T, because you're going to have 2 points in time, 1982 and 1999. You can actually link these households from over these 2 periods. So you have a panel. Okay, on the right-hand side, you have it's the same regressors, again, except that they have the T subscript. And you can now put in a household fixed effect as well. So you have some more power here to pick up for household characteristics, which could determine both migration as well as participation in the network. And when you difference out, you end up with this. Now, the problem is that this will take care of any fixed household characteristic, which determines migration as well as, for example, household income. But there could be shocks to income, which could directly determine migration, for example. I mean, think about village infrastructure. So it could be a story where suddenly in this village, from one year to the next, you suddenly get a bank or something, or a high school or something. A bank is the best one, right? Because all of a sudden your income is going to go up, and your propensity to migrate is going to change as well at the same time. So what you need is some variable which determines the change in income from 1982 to 1999, which is uncorrelated with all these subsequent changes in infrastructure and opportunities to migrate and so forth. Right? And so what we do is, and I think this is not a bad, this is for you all to see, is when you think about an instrumental variable, I'm from a background where all instruments are bad, right, and are never credible. If you went to Harvard, MIT, that kind of would be the kind of story you would get, unless you had really, got it perfectly. But I think, everything said, I think what we use as an instrument here is not such a bad thing. What we take advantage of here is sort of is a technological feature of what is known as the Indian Green Revolution. So this was something which happened in the late 1960s and the 1970s, where they introduced these new varieties of wheat and rice, which had much higher yields. And it increased farm productivity dramatically. Okay, and increased farm incomes as well. But the thing about these new varieties was that you needed irrigation for it to actually function very well. And so what you had here is the interaction of this new technology with irrigation. And so our story, our instrument is that certain places, for example, very early on in the late 1960s, got access to this new HYV variety. And what we're going to argue is that that's endogenous. There must be some reason why they picked those particular places. Certain places at that point in time had access to irrigation. Again, we're going to argue that that's endogenous too. But the interaction of the two, we're going to argue, is just somehow, going to determine the change in income because it's going to have this, this big technological effect. But what we're going to try to argue is that that is not going to directly determine changes in income and changes in migration and so forth. Now, you might think that places which got both, which had irrigation and got the new technology were also different for some reason. And of course, there's nothing we can do to rule that out. But this is kind of where we are with it, okay? And what's nice about this is that we can go back to the first round of the REDS, which is in 1971, and see whether the household's village, the fraction of land that was irrigated, and whether this village actually had this HYV technology. And we can use the interaction of the two as the instrument. It turns out that there is some issue here concerned with the power of these instruments, as you might imagine, because we're using something from 1971 to predict the change in income from 1982 to 1999. But we still do relatively well for some of these outcomes. Now, the main point is, so for example, with migration, I think we do okay. We do terribly with participation. Okay, this F statistic is 2.9. It's just like, you really have to worry about the strength of the instrument. Okay, but if you look at migration, you get the same pattern here that I showed you earlier in the reduced form. But this is a completely different data set, right? This is not the 2006 census. This is from 1982 and 1999. We're instrumenting, we have fixed effects, and you still get the same pattern. Conditional on the household income, as caste income goes up, you're less likely to have migrant members. But now we can look at participation at the same time. Conditional on household income, as caste income goes up, you are less likely to marry outside of your caste. You're more likely to be within your network. And you get the same pattern here for participation, but as I said, we have to be a little worried about this because of the strength of the instruments. But what you're seeing here is direct evidence about this connection, this association between migration and participation in these caste networks. Okay, and then the last thing I want to do is just very quickly, I know we're almost out of time, but I just want to very quickly show you some counterfactual simulations. So this is, which I think is actually kind of nice because we have this set up now. So what we do here is we basically take the relatively wealthy households, and what we do is we reduce their beta. Okay, these are income classes, but forget about what these income classes are. Basically, just imagine that we, and what you find is, not surprising, as the beta goes down, they're going to be more likely to migrate. So the migration of the highest, this is the highest relative income class, it increases from 5% to as much as 25%. Okay, if you look at the lowest income class, it hardly changes at all. But look at the lambda and see what has happened to that lambda. What is happening over here? So basically think about the way the model is set up, right? So when you reduce the beta for those relatively wealthy guys, think about this as like a credit scheme or something, they're all going to start to want to migrate, right? Because now they can leave without losing the service, and still maintain, smooth out their consumption. But when these guys start to leave, then what happens to the income sharing rule? You want those guys to stay because the network is going to lose its ability to smooth consumption when all these people leave. So what you do is you start to reduce the lambda for these guys. The redistribution starts to go down. Now think about what's happening to the lowest income class. Their migration has hardly changed. They are just staying back in the village as they were before. But their consumption is going to go down a lot because of this redistribution. And this just goes to show you that when you're doing program evaluation, for example, you really have to take account of all these underlying institutions. If you just went into this place and gave people a credit, introduced a credit scheme, for example, you would solve one problem here. You would solve the problem that started off this whole paper, which is that you have this problem in the insurance market, which is then spilling over into the labor market. You would solve that problem, and these guys would start to migrate. And you would close the wage gap and do all of those nice things. But guess what? Then you would create this other problem, which is this distributional problem within the network or within the community. And if you don't think of these things, which is often what happens, then you would end up coming up with, if you didn't think about this, you'd be completely foxed. You'd say, why is it that these guys who aren't even treated by this credit program are actually worse off? They're consuming less, unless you think about the spillovers. Okay? So this is basically where I want to stop because I'm over time, but I hope you guys enjoyed this. But as you know, I think what I wanted you all to see was how you can write a paper which has everything, right? I mean, you have theory, you have different types of empirical tests, and as long as you don't care about the methods that you're using, I think the more you do, the more fun you have exploring the world, the more happy you will be. So, okay.